Good morning, everyone. Welcome back. So we'll continue a bit. We'll finish the exploration of the rates for Gaussian process priors. So recall that we saw yesterday that there was a central equation involved, which was very simple, given you have the concentration function of the Gaussian process prior. So recall that the Gaussian process has some RKHS H in B. So for us, either L2 or C0. And you have two parts on this concentration function. The approximation part, so this, which measures how well elements of the RKHS approximate a given function. And the small ball part, which is a sort of measure of complexity of inner complexity of the Gaussian process. Okay, so if you solve this equation in epsilon n, we saw yesterday a result giving you essentially more or less what you have here. So what we saw in the first lecture, the kind of the generic theorem, and we saw yesterday what I call the pre-concentration theorem, which was essentially for Gaussian process priors, something that very much looked like this, and the only extra step to add is just to link distances, because yesterday, so in the pre-concentration theorem, we had here the norm of the Banach space B, so we have to relate this ball, the Kullback-Leibler neighborhood, to the ball in B, and similarly this distance D to the distance in B. Okay, so depending, that's where the statistical model now comes in. So I already mentioned that for Gaussian white noise model, it was very easy. And the reason is that for the Gaussian white noise, we can apply the generic theorem with the L2 distance, and the Kullback-Leibler neighborhood is just an L2 ball. Okay, so it's a ball in L2. Okay. Around theta 0. So here I can, since I work with functions, okay, the parameter here is a function. Okay. All right. So we have immediately we can, from the pre-concentration, from this preliminary theorem on GPs, we can directly apply the generic theorem. Okay. So that gives us so the rate. The posterior concentration rate, so I'll not write the statement, but the posterior concentration concentrates in terms of the L2 norm at the rate epsilon n given, so any rate epsilon n that satisfies this equation with now W naught over there, just the F naught, the true function. So recall we work under the frequentist assumption that there exists a true function f0 that generates the data. Okay, so very, very simple. So if we want to do other models, we can, but we have to work a little bit more. So let me quickly say a word about density estimation before I give some examples of how we can check this rate equation. Okay, so in density estimation, so recall we have just IID data. Okay, so in the Bayesian setting, you would write it like this. So given F, it's IID of density F on 0, 1. And so we saw that, so if we want to use a GP, we cannot use a Gaussian process directly to model density because it's not positive in general. So we can use a normalization. Okay, so for instance, let's take, you could use other normalizations, okay, other functions, but the exponential function is pretty much used, it's quite popular. Okay, so we look at the distribution, so our pi, the prior on densities, is just the distribution that is induced. So I take a GP W and I look at the distribution induced by this transformation and this induces a random density, okay, by the normalization. So this pi is the prion densities induced by this, okay? So if I do that, so then state a little theorem, which is 2.5, I think, in the notes. So now I just have to be a little careful. So since the GP models something at the level of the exponential, actually the W naught I'll use for this equation is rather the logarithm of the density F naught. So in particular, I'll assume that the true density is bounded away from 0 here. So suppose we had this little technical condition. I'll come back quickly to it in a moment. That we have to be in the closure of in B of the KHS H, and that this W naught now solves the equation. Okay. Phi W naught epsilon smaller than n epsilon squared. Then we have that the posterior distribution concentrates, so in which distance? In the Hellinger distance at rate epsilon n. So this goes to 0 for m large enough. Okay, so let's see how we can verify this. So the only thing we have to do with the pre-concentration theorem we proved last time is just to link distances. So we want to find an appropriate distance d in which apply the GGB theorem. Okay, so in the density estimation model, yes.
Could you remember what is h of f and f0?
So it's the Hellinger distance. So Hellinger. Okay. So here is the mu is just Lebesgue. Okay. And so why do I take the Hellinger distance? Because I've noted in the first lecture that I know that it will verify. So I have to choose the distance that verifies t. Okay. And in the density estimation model, we have seen that either Hellinger or L1 distances are automatically satisfy d. Okay. So that's why we take the Hellinger. We could also take the L1, but now I'll just write some inequalities that showed, there is an easy link between the Hellinger, L1 would work actually similarly. Okay, so since, and I didn't say, so B now here is going to be the separable Banach space of continuous functions equipped with the sup norm. And why the sup norm here? Because it's going to be easier to link distances if we just have a control of the sup norm, because the sup norm will dominate essentially all other distances. So the key here is to, so the pre-concentration theorem, so apply the pre-concentration theorem with W0 equal log F naught, so in B, okay, for the Gaussian process. So that gives us things in terms of the the Banach space norm that was in the pre-concentration theorem, therefore it's just a sup norm, okay? And then the only thing you have to do is to, since for this theorem here we have the Hellinger distance and here the Kullback-Leibler, we only need to link the Hellinger with the soup norm. It's enough to bound it from above by the soup norm, but as I said, it will be fine. And express, so include in this, it suffices to include in this Kullback-Leibler neighborhood a soup norm neighborhood, okay? Because the concentration theorem gives us something in the soup norm, okay? And that's just, so I will not prove this, but I guess the intuition is clear. It's in the notes. So this is, it's not too hard to show that you have a control from above in terms of the soup norm. Okay, so for any two, so if you take some functions v and w, so p here, so what is p? P is this transformation, so it is v e to the v divided by the renormalization, and the same for pw. Okay, so I should have written it here actually. So this is p capital W, okay, of t. And so we can link the Hellinger distance between those to the soup norm distance between the log densities here, what's in the exponential on the top, okay? And so this is, say, a big O of V minus W soup norm if V minus W is bounded. Okay. And similarly, it's not difficult to prove that the Kullback, so the Kullback is like a square, so locally, so maybe it's not surprising here to see the soup norm squared, times again some terms that I will not write. It's a big O of V minus W soup norm squared again if we have this. And similarly for the V, so remember this Kullback neighborhood was defined in terms of K and V, and similarly this is a big O of V minus W. Okay, right. And once you have that, then you can just include so the Hellinger, the BKL neighborhoods. So this is for here it is my density F naught contains a ball for the soup norm, so a ball of this type, so a set of W's such that W minus W naught in soup norm is smaller than some constant C epsilon. Okay? And then we are done, okay, because so I'm going a bit fast here, but the idea is just that you only need to link distances and it's fine, okay? So once you have the pre-concentration theorem gives you this, and then the statistical model comes in at the level of you have to link distances, okay? All right, so any questions on this? So it was just to apply this pre-concentration theorem, and now I just quickly give some example of the behavior of this concentration function. Okay. So, sorry. Yes.
How restrictive is this assumption that the W0, the log of f, is in the disclosure?
Yes, thanks. So I'll come back to it. In a second, so thank you, indeed. So it depends on the Gaussian process that you have. So if your Gaussian process is in a sense rich enough, this will be no problem. So we'll see in a second. So for Brownian motion, for instance, it is almost, so if you work in the, like here, for the density estimation in the space of continuous function, the closure is almost the set of continuous functions, except that since Brownian motion starts at 0, you have the constraint that the function must be 0 at 0. But it's easy, so I'll come back to that in a second. it's easy to, so you just have to release Brownian motion as 0 if you want all the functions. But indeed. So examples. Of GPs and of functions phi w. Okay, so let's start with Brownian motion. So the RKHS of Brownian motion is the set of functions which have derivative in L2. So you can write it as this. So it's not too hard to show that the RKHS is the set, you can write it as primitive, so from 0 to dot of functions g's that are in L2. And the RKHS norm, so if for a given function h dot in the RKHS squared, this is just the L2 norm of g. So in particular, note that all these functions, they have the value 0 at 0. Okay? And that just reflects that Brownian motion starts at 0. Okay? And therefore here, h bar in B, okay, so it's, so if we take, here we can take both B L2 or B C0, but if we take C0, like we do for the density estimation application, then we get just the set of continuous functions that are 0 at 0. Okay? And so if you want to avoid that, if you want to have all functions, it's quite easy. You can just, so instead of B, you can define Z to be Bt plus an independent variable y. Okay, and that just releases Brownian motion at 0, and then for this process released at 0, you get the whole space B. Okay, so it's not a big restriction, but indeed one has to pay attention to that. Okay, so that's for the RKHS, and as I mentioned already yesterday, so the small ball probability is well known here. So recall that if I take the function 0 here, so this term is just 0. So this part here, the small ball part, I can write phi 0 of epsilon, this bit here. So this is of the order epsilon minus 2. Okay, so that I mentioned already. And you can, it's not too hard to check because this space is very explicit. Okay, so it's not hard to, so if you want to compute, to have bounds on this term, you are just asking, so if I have a given continuous function which takes the value 0 at 0, okay, because recall we want to have that W naught is in h bar of V. Okay, how well can I approximate this W naught using functions of this type? So functions that are a bit smoother than just continuous, okay, that have one derivative in L2. So that's a type of Sobolev space, and it's kind of by standard argument, so we'll just give the ID. So if, and the little computation is in the node, but it's really kind of little routine computation on convolution, so I'll just, you can just look at it as an exercise, but I guess conceptually it's quite natural. Okay, so if I take some C beta function, so a Hölder function of regularity beta, which takes the value 0 at 0, we have that this term here, so the first one, which maybe we can give a name, we can call it phi a of epsilon, like the approximation part of the concentration function. So phi a of epsilon here is smaller than epsilon to the 2 beta minus 2 over beta maximum 1. And how do you prove that? So ID of proof. So if beta is larger than 1, is at least 1, it's very easy, because then if you are at least C1, then you are in the RKHS. So if you are in the RKHS, this is just a constant, so that's this regime. Okay? So if beta is larger than 1, then W belongs to the RKHS. Okay? So that's very nice. And the other case is, maybe I'll write here, if beta is smaller than 1, you can just take a convolution that approaches, so I can set H sigma of t, which will be like your favorite, say, modifier or kernel, like a Gaussian kernel, for instance, minus, and here you just have to subtract to take a function which takes the value 0 at 0, okay, to be in the RKHS. So this H sigma function, it is very smooth, because here we take, for instance, a Gaussian kernel with a certain bandwidth sigma, and sigma here will go to 0. And you just so W naught in principle is not in the RKHS, so in general is not in the RKHS, but you convolute it with something smooth, so this guy now will belong to the RKHS, and this is just to ensure that the value at 0 is 0, okay? And then it's easy, so with convolutions, so why I take a convolution is because then to compute the norm, the RKHS norm, you just have to take the derivative of this, and this is easy because, well, when you take the derivative of the Gaussian kernel, there is a sigma, a -1 coming out, and you can easily compute this approximation, and you get this other term. Okay? And now what's interesting is to make the sum of the two. So now phi W of epsilon then is smaller than epsilon minus 2, and maximum, because you get the sum of the two, maximum of this epsilon 2 beta minus 2 over beta, maximum 1. Okay, so you get, at the end of the day, what you get is that an epsilon n, so, and you want this to, you want to equal this to n epsilon n squared. To solve the equation, and if you solve this, then you get epsilon n, which is like n minus 1/4 maximum n minus beta over 2. Okay, you can also write minus 1/4 and then minimum beta over 2. Okay. So is this good, bad? So at least it's something, so it gives us some rate. So the posterior, then it means that if you take Brownian motion as a prior function, either in Gaussian regression or in density estimation or in any model where you can do this link of distances, which it means very many models. You could do classification, for instance, okay, many things. You get this rate, okay? So observe that, so what is the best possible rate here is the one where, so if beta is very small, this term wins, okay? So the best is always, so this rate is best for beta equals a half, okay? Because if beta is smaller, you get a worse rate, and if beta is larger, you get n minus 1/4. Okay, and beta is a half may ring a bell compared to the smoothness. Okay, so we said that Brownian motion is essentially one smooth, so one half smooth. So what it means is that if your true regression function, so your true f naught is beta smooth, is a half smooth, by chance, then Brownian motion will, so the rate will be the best here. And if we compare to the optimal rate, and so the minimax rate in this setting, in this type of setting, will be typically n to the minus beta over 2 beta plus 1. Okay, so if you take beta equal a half, then you get n minus 1/4. Okay, and so what it means is that Brownian motion is going to be lead to optimal rate if the true regularity matches the regularity of Brownian motion, but otherwise this rate you can easily see that it's always slower than this one, which means that you have some what we call consistency rate. So you have some rate, but it's not optimal. Okay, so that's both bad and good news. So the good news is that at least you get some concentration, but the concentration rate may not be optimal depending on the regularity. So if you have a very smooth function, and if you use Brownian motion as a prior, then you get some rate, but not the optimal one. Okay. And more generally, let me quickly give more generally, if you take now WT a series prior, so let me just take the usual notation, a Gaussian series prior. Okay, so here I take IID and 0 ones. Then one can check that the rate that one gets is really generalizes Brownian motion, which would be the case, something similar to this, but with alpha equal to a half. So you get alpha inf beta over 2 alpha plus 1. Okay, so it's optimal if and only if, actually, although it would need an extra argument to show that, but it's optimal if and only if alpha equals beta. You can show actually a lower bound that if alpha is not equal to beta, then the rate is suboptimal for certain functions. Okay? So that's both, again, satisfying and a bit disappointing, because you have a rate, but it's optimal only if you match the regularity of the unknown function. So in general, there is no reason why you would know in advance its regularity. So this leads us to an adaptation question. Okay? Because now it's natural to ask, okay, what happens if we don't know the regularity of the true function? Is there a way to, so because it seems now that we have this nice theory for Gaussian processes, but how do you, is there a way to make them adaptive to the unknown regularity in general of the true functions we have? Okay. So now in the lectures, we are going to move in the next today and the next one, we are going to deal with adaptation questions. So you can be adaptive with respect to several things. So one thing is smoothness, regularity, as we see here. And we'll see next time that we can also, there are many statistical problems where you have other types of parameters that can characterize, for instance, sparsity or certain compositional structures for deep neural networks, and we would like to be adaptive to them. And it's natural to ask, okay, can we do that in the Bayesian setting? And we're going to see now that there are very natural ways to just deal with that in the Bayesian setting. And in particular, the tools we have introduced for the proof, so this generic theorem, it becomes quite powerful when we have complex priors, because it may not be much harder. So if you know how to apply the theorem for a basic prior, then if you complexify a bit the prior, the proof is kind of robust. It doesn't, it's not much harder to kind of prove it for the slightly more complex prior. Okay, so I can take questions maybe. Yes?
Maybe it will take too much time, but at several times you mentioned minimax rate.
Yes?
And I personally do not remember what is minimax rate, but I do not know if it takes quarter of an hour.
Sure. No. So I can, it's easy to define. So it's just that, so what we try to do indeed is that to connect this to optimality, we try to obtain for the posterior, since we take a frequentist, we do a frequentist analysis of the posterior, it's natural to try to match the rate we get with what is known to be optimal in the frequentist setting, and this is the minimax. One way of talking about optimality is minimaxity, and that's kind of the canonical way. And then, so the minimax rate is something which is defined as follows. So you have so it's minimax, so it's the inf over all possible estimators T of the soup over your parameter set of E theta. So you have a loss function here, T of x theta. Okay, so that is, say, star. That is the minimax rate for the loss function L over the class capital theta. And here in the context of nonparametric models, for instance in Gaussian regression, then your theta is a set of functions. And what I've been taking for capital theta actually here is, so maybe the notation is a bit, I should write maybe a different, maybe here it's easier actually if I write a function like here, like this, okay, so that because we are in a nonparametric setting. So the type of class I've been taking here is a Sobolev ball or a Hölder ball. And if you take a Sobolev or a Hölder ball here in these settings, what you get is, and if the loss is a L2 loss, or you could also take the L infinity loss, but then you get an extra log, is something which is of the order, so now I put a different sign because I allow some logs. Okay, so you get a rate of this type if F is a beta Sobolev ball or beta Hölder ball, depending on the setting situation. Okay.
Thank you.
Sure. No, but that's indeed important. So I don't have too much time to explain this, but it's kind of a different part of statistics. But you can take just it as granted that the target rate, I just give it to you. Okay. So other questions? Okay. So now we are going to talk about, as I said, adaptation smoothness. So let's, to fix ideas, let's have in mind that we have this, I'll write P alpha for this Gaussian process, this series prior, okay, which is on the right-hand side. Well, actually, let me. Okay, so I have actually a family of priors, pi alpha indexed by alpha. So here alpha is just a positive, okay? And I'd like to pick alpha in, so if I would know in advance what beta is, I would just take alpha equals beta, okay? So here the natural idea statistically is that you'd like in a sense to take maybe a data-driven alpha so that you can adapt automatically to the unknown beta. Okay, so then you have two very popular natural approach. And one, since we're in the Bayesian setting, remember, everything that's unknown, we can just take it random, okay? So first thing we can think of is just, well, we don't know alpha, let's just put an extra prior on alpha, Okay, so let's just make alpha random. All right, so formally it means that you draw alpha according to some prior, let's say, little pi, and then you draw your function according, for instance, to your Gaussian series prior. Okay. All right, so then actually, so that's called hierarchical base because you have a prior and you have a second prior on the top, a hierarchy of prior, and then in fact it's just, you can think of it as just a special prior on the original function. It's just a mixture. Okay, so it's a mixture over these pi alphas. D small pi of alpha. Okay, so you just get a mixture prior. So since it's a special case of prior, you can just as well use the GGV generic theorem. Okay, and indeed that's what we are going to do. That's what we can do to handle this hierarchical base. It's just a natural. It's very natural within the Bayesian framework. There is another approach which is also popular in practice because sometimes it's also quite fast to compute, and it is empirical base. And so what does empirical base mean? It means that instead of taking alpha random, I just take any data-driven alpha I like, I just put here alpha hat. So take alpha hat equals alpha hat of x of your choice. So anything, any measurable function of the data, any estimator of alpha you may take. Okay. So now, of course, the question is how do you choose? How do you take this alpha in general? So then there are various possibilities depending on the model, but a kind of a generic approach is what's called the marginal maximum likelihood. So in a sense, it's a bit hybrid between base and MLE. So you do base, but for the tuning parameter, you do MLE. Okay, but what is the likelihood here? So in the Bayesian setting, there is a natural way to define a likelihood on alpha, and it's just to take the marginal likelihood of the data in the Bayesian model. Okay, so recall that so in the Bayesian model you have x given f that is the model, and then f is now pi alpha. Okay, so so that's the Bayesian model. So if you marginalize, so if you look at the distribution, the marginal distribution of x, okay, so that gives you the law of the pair. If you look at the first coordinate, you'll just get a formula, just the integral, which I will write now. So it's the integral of your original likelihood against simply the prior. And the prior depends on alpha. Okay. So here I integrate out the f, and so I have something that only depends on x and on the alpha. Okay, so I do that for any alpha. It's a function of alpha and the data, and I just take the argmax of this in alpha. Okay, so that's called MMLE estimate, marginal maximum likelihood. And then to make inference, then I work with a plugin posterior, okay, which is this object. The posterior where I plug in alpha hat of x in for the alpha. So here it's a little bit more tricky because your prior now depends on the data. So if you, in particular, you cannot, in principle, you cannot apply the GGV approach because that's for a fixed prior or independent prior but non-data dependent prior. So there are ways, there are a few generic results. In particular, there is a result a few years ago by Rousseau and Szabo, where they provide some tools to, so essentially they generalize a bit the GGV, so they kind of provide tools to make the GDV work also in this setting of MMLE, where your prior is alpha is data dependent. Okay, so those are two options, two general options to make adaptation. Okay, and now let's see how it works in specific situations. So let's take our two examples of last time. Random histograms. So recall that, last time we say, okay, suppose we pick some heights at random, so that gives a random histogram. But we had to choose k, right? So here we had like a regular histogram on k-bins, and last time I said, okay, take k to be, so the good k was essentially this one. So if I know beta, I put beta here, or I called it alpha maybe yesterday, but it doesn't matter. And if I would know beta, I would take this choice of k. Okay, but the problem is that in general we don't know beta, so we can take beta random, or equivalently we can just make k random. Okay, so just make k random. So draw k according to some prior little pi k, and given k, we just take the same prior as yesterday. Okay, so it's just the law of certain sum hk capital K indicator of these regular histograms. Okay, so there are k-bins, capital K-bins, with here hk, which are drawn independently. So just for instance, Laplace 1 tensor k. Okay, just independent Laplace as we did last time. Okay, so that's a very natural choice. Okay, we don't know k, we just put a prior in it. And what prior do we put? So to make it nice and so that it combines nicely with the generic theorem where you need this exponential decrease, it's natural to take a prior that decreases exponentially. So here you can take either e to the minus k or something like e to the minus k log k is also a frequent choice. Okay, so something exponentially decreasing, you don't want to put something too fast, like k squared would be too fast here, but something exponentially decreasing is typically very nice. Okay, and now let's see what happens. Okay, so if we do this, we are going to get a little theorem. So in the Gaussian white noise model, so if we assume that f naught, like the last time, is beta regular, the same class we took for some beta in 0, 1. So beta 0, 1 is because we have histograms. We don't go beyond regularity 1. Then for this mixture prior, for pi, so if I call this prior pi h, like hierarchical prior, get posterior convergence. So I don't rewrite the statement, it's the usual statement. So in the L2 distance, the L2 norm, at rate so up to a log term, it's the minimax rate of estimation. And well, you have a constant here in front. Okay, so this means that you get adaptation automatically with this hierarchical base approach because the prior pH doesn't use any information about the smoothness beta, and yet it gets the optimal rate. Okay, and the proof is actually very easy. So it's once you have done the proof for fixed k, it's really the same. So you just put into the machine exactly the estimates that you had for fixed k, and you just add one layer of hierarchy. And it just means adding 2 lines, essentially 1 line or 2 per, so for each of the conditions. So here, I just, for illustration, let's see how we handle the prior mass condition. And the other 2 conditions, entropy and sieve, are just very similar again. Just so let's do the prior mass. Okay, so we want to bound from below. So we are in the Gaussian white noise model. So the Kullback-Leibler is just this. It's just an L2 neighborhood, and we want to bound this from below. Okay, so what we do in all these cases is that, well, we just need to bound this prior mass from below, so we can just take the k that is nice for us, which is the k from we already used in the proof last time. So to do that, we just said that this is larger than the probability that we have this, and capital K equals to Kn for our favorite Kn. Okay, so I can just say that, so this is the same, well, this is bounded from below by this. Small pi k of k equals Kn. Okay, so small pi k, it's a discrete prior here on the integers. So here, this probability is nothing but the intersection of the event this is smaller than epsilon n and k equals to Kn. Okay, and now this I know what it is, because I choose the prior, I take an exponential decrease. So suppose we take, for instance, the second one, get Kn minus Kn log Kn. Okay, and what is Kn here? So the natural Kn is the one we already saw last time. Okay, so it's n over log n, or you can remove the log n if you like, you just get a different log n factor here, 1 over 2 beta, or 1 plus 2 beta. Okay. Yes?
What's the symbol small p in this case?
What's this small pk here? Yeah. So it is just this this small p. Oh. So it's just a prior on the integral. So sorry, I didn't write it exactly the same. So it's small pi. So generally I make it a little wiggly to illustrate that it's different from the capital pi. But, okay. So here is just the intersection of event. Okay, so the probability is smaller. And then this is exactly what we already computed. Okay, because this we already did in the proof, or we already bounded it from below. Last time, right? And what did we get? We get, so I can just copy from last time, we get exponential minus Kn log 1 over C epsilon n minus, and that's it. Okay? So you see that when you multiply both terms, they are both of the same type. Okay? So what you get here is just that the prior mass is bounded from below by some exponential term, exponential minus k, a constant and a certain log. I can put log n actually, because so epsilon n, and both epsilon n and kn are powers of n. So I just get this, and this is very nice because it's exactly what I want for the application in the DGV theorem, exactly like last time, okay? Because last time I had this, which is also of this form. Okay, so the prior mass condition is checked. Entropy and prior mass, entropy and sieve are also okay, because so entropy, I just take the union of sets up to Kn. So the sieve, sorry, first, the sieve, I just take all sets of histograms that are bounded, recall like yesterday, but with k smaller than kn. Okay, and I can do that because the probability of being larger than kn is going to be exponentially small. So I can throw it away. So that's okay. And entropy, I just take the union up to k equals to kn of the sets we looked at last time. And so then it's additive, and I just get an entropy which is of similar order. Okay, so you can look, I mean, it's in the notes, of course, you can check the details, but really the main idea is this one. Is that for prior mass, you see that it's not much more difficult once you put here a prior on the smoothness parameter that is kind of compatible with this exponential rate that you want, then it works nicely. Okay, so all right, so that's for the simple example of random histograms, and now we'll see some other priors. Yes?
Could you comment a bit on the choice of the prior on capital K? Because, I mean, as I understood, you say this exponential decrease is rather kind of a technical condition. Because as far as I know, in very generic Bayesian setting, for instance, Solomon inference and so on, you tend to expect better results when the prior is extremely slowly decreasing. And here it decreases rather sharply, so I'm surprised.
Yes.
Are there deep reasons
No, that's a good point. So if you want to, to apply the GGV approach, here actually it's for the, so maybe this wasn't clear before, I think I mentioned it for the prior mass, but it's rather for the sieve that you need this exponential decrease. So it's for the sieve here that you are going to need that the prior decreases fast enough so that you can drop it at exponential rate, okay? But if you absolutely prefer a prior that goes slowly, let's just do alpha tempered posteriors. So if you use these alpha posteriors that I mentioned yesterday, you only need to check prior mass, and then here you can put any decrease you like. So here this is going to hurt you only if the decrease is much too fast, because then the prior mass can be too small. But if this is relatively slow, that's no problem for the prior mass. Okay, so if you
not silly to have a slowly decreasing prior.
No, not necessarily. No. It's just that here technically it helps to have absolutely, yeah, sure. But that's a good point indeed. That's a bit of the that's a limitation of the. But it's a non-trivial question to know for a given problem what are all the priors that work actually, that provably work, and. In many of these nonparametric contexts, it's not so clear. So what happens? So if you take a given prior that maybe that doesn't decrease too fast. So yeah. So the GGV theorem is how it is. So if you want to apply it in certain settings, you will need some fast decrease just to be able to remove some sets, like to verify the sieve condition. Okay. So let me move now to adaptation for series priors, for GP series priors. Okay, so now again, so I erased it, but so we kind of are used to it now. So it's just the minus a half minus alpha, zeta j, ej. Okay, so here you can do exactly the same. So you can do hierarchical base. So you draw alpha, for instance, you take an exponential, standard exponential distribution. And so again, note indeed that here I take exponential tails, which is convenient to verify the GGV condition. And here I take P, given alpha, I take this P alpha. So here there are several papers that consider this, and you can show that the rate So in particular, Szabo, van der Waart, and van Zanten proved that the rate in a regression, say, posterior rate that you get is the correct one. So it's of the order, the logs, there is a log term, and then n to the minus beta over 2 beta plus 1. Okay, so this prior is completely adaptive. Okay, so recall that if you just take this one with a fixed alpha, you get this rate I wrote before with the alpha in beta over 2 alpha plus 1. And here, just by taking alpha random, you get automatic adaptation. Okay, so I'll not write the formal statement. So you can do also empirical base. So maybe in the interest of time, let me go a bit quickly over it. So you can just compute here. So if you have this likelihood, this marginal likelihood here, you have an explicit expression of it in white noise. So it's not very difficult. It's a few lines of just Gaussian computations. So you have, let me maybe just write it just to show you that it's fairly explicit. So here it's white noise model. Okay. You could do that also in density estimation, but then actually empirical base becomes a bit more complicated, but it's also possible to do it. So in white noise, the advantage is that you have explicit expressions which you can maximize just very easily on a computer in terms of alpha. You don't need to do any MCMC or any fancy posterior sampling method. So here, this is the log marginal likelihood. Okay, so it's an explicit expression, and I can take alpha hat of x equal to the argmax of ln of alpha. So actually, they don't take it over the whole R plus. They actually stop because at log n, sometimes there are small boundary problems. I mean, technically, it's just a technicality here. You want just to allow, since the interval grows to the whole real positive real line, it doesn't matter. Okay, so then again, with this empirical base, you get again the rate, the optimal rate up to a log factor. Okay, so that's nice. Yes. So it's just an explicit function. So, and then of course it's infinite, but typically you truncate. So you would just truncate it at n, say. So I mean, you can prove that truncating it doesn't hurt you because anything. So in nonparametric problems, anything that's beyond the frequency n, typically you can put it in the bias. It doesn't matter. And here, so I don't remember exactly. I don't remember if they really proved that you can take n here, but I'm sure it holds. And probably in practice, anyways, on a computer, you have to cut somewhere. But,
okay, but even if you cut, you can show that the maximum.
Yeah, it will just behave similarly. So yes. So in the paper, maybe they took up to infinity, but I'm sure it will work as well. But when I'm saying it's simple, it's just that you have an explicit expression. It's just that if you would do that in density estimation, you would have something much more complicated with integrals. So you don't have to compute any integral here because the integrals have already been computed because it's Gaussian, and that's the result. That's what I mean by it's completely explicit. Okay. So then there are technicalities that it's an infinite sum, etc. That's something else. But yeah, thanks. Other questions? Okay. So let's. So nice. So let me show you now another. So today we see quite a few examples. Adaptation using another idea, which is scaling. So in machine learning, as I already mentioned, I think a very popular Gaussian process is the so-called squared exponential Gaussian process, and it is a Gaussian process Z. So we always take Gaussian centered Gaussian processes, and the covariance kernel is just an exponential with a square. Okay, so here I allow some parameter a s minus t squared. Okay, so this s squared exponential a. So that's a very popular Gaussian process prior. So if you look at the paths of this process, it's something, as opposed to Brownian motion, is something very smooth. And it reflects that k is very smooth as well. So if you have a path of the process like this, okay, so let's say that this is z with a equals 1. So you may think, okay, let's just take a equals 1, okay, but or a fixed. So if you do that, what happens? Let me give you the. So we know it's from what we saw last time and from what's on the board now, that to compute a rate of convergence for the Gaussian process posterior, so for the posterior corresponding to taking a Gaussian process prior, it's enough to solve this equation, okay, with the concentration function. And let me just give you the small ball probability. It's kind of expected that the small ball probability, so this looks very different from Brownian motion, so probably the small ball probability is very different, and indeed it grows very slowly, just reflecting the fact that it's a very smooth process. So if I look at phi naught, so little a now, so not the approximation part, but it's just that it depends on a. Well, let me just not write it, but for now, so the small ball term, okay, so minus log p sup norm of z smaller than epsilon. Okay, so this is smaller than a certain constant a log a over epsilon to the power 2. Okay, so recall, so for Brownian motion here you get epsilon minus 2. So it grows, the minus log of the small ball probability grows much, much slower. So is it good? Well, not that good. Well, maybe the bad news is this is very slow. So the process, it reflects the fact that the ZT is very smooth. So you can, it's actually possible to show a lower bound. So if you use Z, which depends on A, right, of dot, there are functions for which the convergence rate is as slow as logarithmic. Some power L here, which I don't remember, doesn't matter. It's not, so you would like to have this n to the minus beta of a 2 beta plus 1 rate, and you get something super slow, you get a logarithmic rate. And it just reflects that the process is very smooth. And so when you see this, you say it's really strange because people in machine learning, they are using this all the time and they claim very good results. And actually, what happens is that they don't do exactly this. So they don't do ZA because they know it's too small. So what people do is that you try to adapt A, you try to take a data-driven A to make the process more adaptive. And so what does it mean? So on the picture, it means that if you want to be able to adapt to possibly not too smooth functions, you could take a large A. So if you take a large A, it corresponds to, so if you can do that just with scaling. So you can note that this is also the covariance kernel associated. So if Z is a squared exponential 1, as I plotted here, if I look at Z of A dot, okay, so Z of AT, it will be distributed as squared exponential a. Okay? And what you do is that you accelerate time. Okay? So when you take a large a, you get something which is more, so if I would continue the path, you get something more wiggly. All right? And that's what you want if you want to model rougher functions. And there is also maybe let it mention, since we are talking about scaling, there is another effect you could consider, which is the other way around. You could think maybe it could be helpful in some situations to take a very small. And this would correspond to kind of freezing the path, right? So if I decelerate time, so okay, so in the limit it would almost be a constant, okay? So that's something that we'll use later, next time actually. Okay, so here what we want is rather to make the process rougher. Okay. So the good news now is well, okay, we are in Bayesian setting. Let's just take a random, right? We want to adapt. So we could do alpha hat, a hat, sorry, to take a data dependent a, calibrate it, for instance, in an empirical based way. Let's just take it random, okay? So you can do both. So for instance, let's take an exponential 1 distribution and then z given a, let's just take squared exponential a, okay, which is the distribution actually of z of a dot, okay, if z is squared exponential 1. Okay, and that works. So theorem, result by Van der Waart and Van Zanten of 2009, I think. So if you take a beta Hölder function, then you get the rate. So just forget about this notation, just think of beta smooth, beta Hölder. You get the correct rate up to a log. So with some wavelets, with some waves, and minus beta over 2 beta plus 1. Okay. And so how do you prove it? Well, you can just use the generic GGV approach. So it's a whole paper, so it is not trivial. So what is not trivial is, so you have to actually, the most important thing here is that you have to make everything, you have to keep the dependency small a. Dependency small a is really key here. So I think the small ball was more or less known for fixed a, but then here you had to work to make really the dependence on a explicit. So how do you prove this type of things? So for GPs, there are generic tools showing that the small ball probability is actually linked to the entropy of the unit ball of the RKHS. So then by kind of entropy arguments, you can show this. And then you can verify so that's quite some work. So you have to find out the RKHS in terms of A, the small ball, the entropy of the unit ball, and then you get something like this. And after this, you can apply the GGV result, and you get automatic adaptation. Okay, so we see that in a sense, extra, so what is kind of the takeaway of this is that extra randomness makes the prior more flexible, okay? Because a given GP, it always suffers from the fact that it will be limited by its intrinsic regularity for adaptation. So just making the extra parameters random typically will lead to adaptation to smoothness, to more flexible priors, which are no more, of course, when you do this, you get a mixture of GPs. It's not a GP anymore, but you get something more flexible that leads to adaptation. Okay. All right. So I'm not proving this, but so I as an exercise at the end of the chapter of the notes, so if you take this as granted plus the approximation term, then you can get a result quite easily for the fractional posterior. So I let it as an exercise, and it's just a few lines where you just combine this, so you can have a look, or otherwise you can look also at the paper. Yes?
For these like adaptive methods, are there no conditions on the data? Because let's say in the data I have something very rough, then
Sure. So here, so here it's for the, so okay, so yes, I didn't say what is the model here. So this is true for, so you can do any like Gaussian regression model, or you can do density estimation or classification, any standard model, and then you need, of course, an assumption on the truth, okay? So of course, you could imagine a situation where you don't have f naughts, for instance, in this class, but very functions in a different, with very wiggly functions, which are not Euler, or with local inhomogeneities, or things like this, where this type of prior wouldn't be appropriate. And I'll come to that actually a bit later today. Thanks. Yes?
Okay. So you mentioned this is very popular in machine learning. Is there, so what makes this process special?
Well, I guess it's the paths are quite smooth, and so it makes nice pictures. Because for Brownian motion, you have something which is a bit wilder, right? So, well, that's how I view it. Probably there are other reasons as well, but.
Because I'm sort of thinking there's a lot of results, I think, of the form. If you take a very large neural network, you sort of randomly initialize your weights, then it kind of looks a little bit like a Gaussian process, at least in the limit. So I don't know if there's some special relation to how, because this is so smooth, how it relates to then some properties of the network.
Maybe. So I'll talk a little bit about the connection, but very briefly in the next lecture about also deep neural networks and also deep GPs. So we can move. We can discuss that maybe for the next one. But yeah, that's a good question. Sure. Yes.
Maybe I didn't understand well, but just to come back on the lower bound.
Yes.
So if you take a small a to be constant, even if we try to estimate, let's say, an analytic function, we will get this bad rate?
No. So that's a good point. So the lower bound is for, I just say it, so maybe it was, I didn't write it. So it's for certain functions. So here, the function for which you get this bad rate is an relatively irregular function at the boundary. It's still Hölder, but at the boundary of the Hölder class. So you can think of it as a beta Hölder function, but not a beta plus 1 Hölder or something like this. You can also show results for analytic functions for these processes. And of course, so if your original function is analytic, actually, since, as can be maybe expected, so since the paths are analytic themselves, you get kind of nearly optimal rates for analytic functions without having to take a random. Yeah, there was maybe another question? No? Yes?
Can you remind me what is the adaptive process taken by frequentism?
Sorry,
This adaptive process, adaptive estimation.
So what is adaptive estimation?
Frequentist way of doing.
Okay. So so there are many possible methods that you can consider. So there are model selection methods. There are thresholding methods, Lepsky's methods. So this is not the only way you can get adaptation. Okay. But so a motivation for doing this is also in terms of thinking of that maybe it can give things about uncertainty quantification, for instance. So I'll come back to that a bit later. But sure, so there are other ways to get adaptation. So this squared exponential is nice. So as we said, it makes nice pictures. So let's could we not use it in maybe a bit more complicated or a bit more complex situations? So one situation I mentioned at the beginning of the lectures was the one, for instance, where you have data on a certain geometric object, for instance, we can call geometric GP priors. So suppose, for instance, you have a certain set M, like think of the sphere, okay, and that you have data on the sphere. Okay, so here it would correspond to the problem of density estimation of the sphere. on the sphere. Okay, so many points here means that probably the density is higher around these points. Okay, suppose take as, just to fix IDs, you take the sphere S2 in R3. Okay, so the question would be, what is a natural GP Gaussian process on M? And naturally, since we have these nice looking pictures, what is the, maybe can we define the squared exponential on M? Okay, on the sphere, say. So a first idea is say, okay, so here M, we can equip it with a certain distance. So for instance, so rho distance on M. And here on the sphere, let's just take the geodesic distance. Okay. So geodesic distance just means, okay, so if there are 2 points here, you just take along an arc here up, and this defines a natural distance on the sphere. Okay, so the first idea is to say, okay, it's easy. Let's just mimic this. So we could tentatively, for now, try to set covariance, which would be exponential minus rho st. So the distance now between 2 points, so S and T are now on the sphere. And I just take the geodesic distance between S and T squared. Okay, so that would be a natural analog of this. Well, there is an issue with this, is that it's not positive definite in general. Okay, so we cannot do this. Okay, so now let's try to see if we can still define something that would look like the squared exponential Gaussian process. And to do that, I'm going to need to do something that Felix yesterday said he didn't want to venture into, which is doing something which has to do with, on the sphere, spherical harmonics. Okay, so there is something which is a natural quantity, natural geometric quantity on, say, the sphere, or more generally on Riemannian compact manifolds without boundary, which is the heat kernel. So very quickly, what's the idea? So suppose you are given an operator on M, and here a natural operator is the Laplacian, or minus the Laplacian on M. And we are going to assume that L admits a spectrum. So for the Laplacian on the sphere, it's well known that the properties I'm going to write now are satisfied. Admits a discrete spectrum with, so eigenspaces HK, so they are finite dimensional, EKL, for L of a certain fixed dimension, which may depend on, so here on K, sorry. Okay, so with eigenvalues lambda K. Okay, so those guys here are eigenvectors corresponding to this eigenspace. Okay, so here what that means is that L of EKL is equal to lambda K EKL. Okay, just eigenvalue and eigenvector. And one also assumes that those guys are continuous on M. Okay, so if you have this, you can define now a positive definite function pt x of y, which is a certain infinite sum. So infinite sum of e minus t lambda k, sum of ekl x, ekl y of sum over L. Okay? And so on the sphere, this is just a kind of an harmonic analysis on the sphere, and you can take, so there are various versions of them, but you can, that's called spherical harmonics, this EKL. And so if you do that, you can set pt xy, so why not? So you can check that it's easy to check that it's positive definite. And you can then take a Gaussian process with this, centered with this covariance. And why is it called heat kernel? Is because, so if you differentiate informally, you see that if you differentiate with respect to time, so this pt is a solution of this of the heat equation. dg over dt is equal to minus Lg. Okay, so minus Lg, which is also the Laplacian g. Okay, so you just differentiate. Okay, and so then this leads to a canonical GP on M. So how do we define it? So to have a GP which has this covariance, we just take sum over k, sum over L, e minus t lambda k over 2, and then just IID variables, which here I call ELK, and then the spherical harmonics, or more generally the harmonics you'll get on your space M. Okay, so those IID M01. Okay, and this Gaussian process has covariance kernel this. Okay, and then so if you want a prior that will be adaptive for your density estimation problem, you can just take P. Well, the smoothness parameter here is just the T. So what you see here is that in dimension 1, you had this acceleration of paths. So essentially what you were doing is that you were applying some time acceleration on the space domain as well. Okay, so both are mixed. Here, in a sense, you decouple the space domain and the time domain, and you make the randomness here then on T. So that will be the smoothness parameter. Okay, so T, I take it random. T according to some density, so you have to choose it well. So here, again, to be able to apply the GGV theory, it's nice to have something that has an exponential decrease. So here we did the dimension. So for the sphere, it would be 2. The intrinsic dimension. We took something like this. So that's something we did a few years ago with Dominique Picard and Gérard Carcacharian. We took this prior G, and then the prior here is just WT. Okay, so a random solution of the heat equation, a Gaussian one, and then you take a mixture of those by making the time random. Okay, and that leads to a rate optimal up to logs. So again, n to the minus beta over 2 beta plus 1. Okay. And now there is still a missing piece. I didn't tell you why this is. This has something to do with squared exponential processes, or because here it seems we cannot define it. And this is kind of some fact that is quite that deeply kind of connects the geometry of M with, in a sense, with probability, and is the fact that the heat kernel, you can show so-called sub-Gaussian estimates for the heat kernel. And in great generality, so not only for the sphere, but for many, essentially when you have a compact manifold without boundary, you can show that this heat kernel has this behavior. So T to the minus D over 2, E to the minus C2 rho, so the geodesic distance here on the sphere divided by t, t minus d over 2, e minus c1 rho squared xy divided by t. So here you see that even though pt is not a kernel, a proper kernel, it's upper and lower bounded by something which is what we wanted to use as a kernel, okay, which is the squared exponential. So in this sense, this is kind of the natural squared exponential on the sphere or on a geometric object. Okay. All right, and the way you prove this is, again, you go through the small ball probability and approximation term. So for that, you need to, so the RKHS of this is very easy. It's a bit like for this. So yesterday there was a question about can you do fast decreases here? And here you see that for this series prior, you see that this decreased quite fast. Okay. For the sphere, this is actually equal to k plus 1, something like this. This decreases very fast, and the RKHS is then a space of very smooth functions. And but what leads you to adaptation is the fact that you can make t random. Okay, and so maybe to conclude, also because now I'm talking quite a bit about this series prior, which again I think I mentioned the first day that they are actually quite used in practice, even so. For instance, in this gravitational waves applications, they use also this Gaussian series priors. So, but maybe Gaussian is not, because I'm talking about series priors, but I didn't mention that much. So, what about taking heavier tails? So heavy-tailed series prior. So maybe let me just give the result, and maybe I'll give a sketch of the proof next time. So why would you possibly be interested in taking heavier tails? So why not? Mathematically, it's an interesting question, but actually in practice it's also relevant. So people look at it in particular in inverse problems, because they noted that if you take, instead of Gaussian, you take something like a Laplace distribution, you get a prior that is more kind of more adaptive to possible inhomogeneities in your signal. So in a sense, Gaussian process is quite homogeneous. So could we take this different from Gaussians? In particular, can we take heavier tails? And if so, what happens? So there were not many results until quite recently. So there is a recent results by Sergius Agapiou and co-authors, I think maybe 2 or 3 years ago. Who took here, who actually generalized this theory with the concentration function for the GPs to p exponential priors. So what's a p exponential prior is just, so if zeta j has density proportional to exponential minus x in absolute value to the p between 1 and 2. That's important for them because they use actually log concavity, so they can go up to Laplace. So p equals 1 corresponds to Laplace. And that's not, I mean, people particularly in imaging were quite interested in the Laplace, but also in heavier tails. But actually this result gives up to Laplace. And what do you get as a rate? So the rate that you get is then something like this. So the first rate is similar to the one we got before. So if the prior is less regular than the true function, you get an undersmoothing rate, this one, n minus alpha over 2 alpha plus 1, which we got also for Gaussian positive prior. But now something interesting happens in the other situation. So if beta is smaller than alpha, you get minus 2 beta over 2 beta plus 1 plus p alpha minus beta. Okay, so that's if alpha is larger than beta, so that's the oversmoothing case. So you get an improvement. So for GP, so the Gaussian process is a case p equals 2. So for p equals 2 here, you get 2 alpha plus 1. But for p equals 1, for the Laplace, you get something better. You get 1 plus alpha plus beta. Okay? So this kind of improves on the Gaussian rate, okay, for the fixed parameter. Okay, so that's something curious, and also you can show that it's also a bit better than Gaussian in the sense that you can also adapt to, so you have good results also on classes of functions with local homogeneities, inhomogeneities. Okay, and so note that there is something tempting to do here. This rate is actually curious. Because so here it's for p from 1 to 2, but what would one like to do here? So what happens if I send this to 0? Of course I'm not allowed, but suppose I send this to 0, then I don't have this, and what do I get? The optimal rate for free. Okay, so it seems that at least if I would be allowed to do that for p equals 0, I get adaptation for free. And that's actually what happens. So in current work with Sergius Agapiou, we prove the following, and I'll finish there. We prove that if we take here heavy tails, you get, in a sense, adaptation for free without having to draw this extra variable to make the prior more flexible. Okay, so suppose so I'm stating really the simplest result just to fix IDs. Take as H, so this density of the zeta. Take H to be a certain heavy tail density, say student with 3 degrees of freedom. Okay, so it means that h of x in the tails will be like x minus 4. You can actually take Cauchy, but it complicates a little bit more the proof, but it also works. So take this and take sigma k. So to remove this problem, so if you do this with the decrease, which is like j minus a half minus alpha, then you get exactly this formula. And if you want to avoid this problem to have adaptation only on one side of beta, you can just make here, it works to take sigma a little bit faster than polynomial. So you can take this, and the result is then, so theorem, so if f naught is Sobolev, so here in white note, is Sobolev beta, Sobolev beta ball, then the rate is automatically up to a log factor. This one, the optimal one, up to a log. And that's nice because so you get adaptation with a lot of, so for free, in the sense that it's actually the heavy tails that allow for adaptation. There's a combination of the heavy tails and of the sigma decreasing fast that allow for adaptation. And when I say for free here, of course it's never for free, but because here you have heavy tails, so it's maybe slightly more complicated than Gaussian, but you don't have to do this mixing parameter, which in practice, often you need to do some Gibbs algorithm, something to simulate from the posterior distribution on this A parameter, for instance, in the Gaussian process prior. Here, you don't need to do that. You just use your simple series prior just with heavier tails. And yeah, I'll stop here. Thank you.